Well, now we're going to try to make what we know of the derivative of vector valued functions into some use for those studying physics. I think that's more physics majors I've seen in one room at one time, ever in my entire life. Well, I'll look at this first in r squared, but then we'll eventually look at it in r cubed, 3 space. And everything I say in r squared is still pertinent in r cubed. So suppose we wish to find the velocity of an object tracing the path of this vector valued function in 2 space. And we want to find its direction or its velocity at a point P. So since the vector is itself x of ti plus y of tj, we can imagine the point moves a little bit further beyond P to a point Q, which is x of t plus delta t, y of t plus delta t. So it's just a little bit further along on the curve. As the delta t approaches 0, the direction of the vector PQ, notated delta r, approaches the direction of motion at time t when the function is at the point P. So in other words, it's the instantaneous direction, if you wanted to call it that. So if the limit as delta t approaches 0 exists, as such a limit exists, then the velocity vector can be expressed as r prime of t, since the definition is identical, and I'll show you how that works out. Delta r is r of t plus delta t minus r of t, and so delta r divided by delta t is r of t plus delta t minus r of t over t, and r prime of t is in fact that limit as delta t approaches 0. So that vector, the velocity vector, is tangent to the curve at P and points in the direction of motion at P. So it's not just the instantaneous rate of change, it's the instantaneous direction. And the magnitude of this vector is the speed of the object at time t. Magnitude meaning, suppose we get a vector that's pointed in a negative direction, then its magnitude would be its length. So here's a story about speed. Speed is the magnitude of the vector r prime of t, which is the square root of the x of t squared plus y of t squared. Actually, that should be, pardon my typo here, x prime of t, y prime of t squared. Now if we were in 3 space, this would be plus z prime of t squared, but you understand that, I think, and it's not really much different. As in regular 2-dimensional calculus, the derivative of the velocity vector is acceleration. And so the acceleration vector is the second derivative of the vector value function r of t describing the curve or the position of the object at time t. Its second derivative is the acceleration. So velocity acceleration in r squared and r cubed, if x, y, and z are twice differentiable functions of t, and r of t equals x of ti plus y of tj plus z of tk, then the velocity vector, acceleration, and speed are given by the following in r cubed, and in r squared just ignore the z of tk and similar. Velocity is r prime of t, so x prime of ti plus y prime of tj plus z prime of tk. And acceleration is r double prime of t, which is x double prime of ti plus y double prime of tj plus z double prime of tk, just as you would have expected. And the speed is this, except with the plus z prime of t squared added into the radical if we're in 3 space.